Thank you. So thanks again. Let's move on to Wendy Mao. So if we could go to her talk, that will be on synchrotron and XFEL studies of Earth's deep interior. Uh, Here we go.
I won't thank Suki again, although I still am very thankful to her and the organizers. And thank you for all these talks. And it's been really exciting hearing about all of the work that's being done in the high pressure earth science community on X-ray facilities. All right. So I set up my talk to present first a few examples of synchrotron studies from our group, and then I'll present some XFEL opportunities that we participated in. And finally, I'll just make some remarks looking ahead to the future. Okay, so first a few examples to give you a flavor of the type of high pressure earth science studies our group has been using at synchrotron facilities. And this first example is mainly just to give you an example of where we use a suite of multiple X-ray techniques to look at one problem. So this is the example of what happens when you mix iron and water at high pressures and temperatures. So a former postdoc in our group, Jean Liu, looked at iron plus water down to core mantle boundary conditions and at more moderate pressures, so below 80 GPa, in agreement with previous literature, he found that iron reacts with water to form wustite and iron hydride. But then at pressures greater than 80 GPa, there's an unexpected reaction between water and iron that occurred. And then he found in an oxygen-rich phase of hydrogen-bearing iron oxide, FeO2HX, because there can be variable hydrogen from 0 to 1, and along with some iron hydride. So you can see in the diffraction pattern on the right, these products. This new iron-bearing hydrogen-bearing iron oxide has very similar structure to pyrite. And if you think about the periodic table, oxygen sits right above sulfur. So the structure is basically the same as FeS2, but with oxygen replacing sulfur in the lattice. Okay, so we measured diffraction. We also wanted to look at the oxidation state of iron and oxygen in this compound. So Jean collected a number of X-ray absorption spectra on the FeO2H and also the hydrogen-free version, just FeO2, and a number of iron standards. And here's a plot of the first derivative of the absorption edge. And so the peak for this FeO2 compound lines up very well with Fe2 plus compared to more reduced Fe0 or more oxidized Fe3 plus, Fe4 plus. And then if this iron is closer to ferrous iron, then it also suggests for our charge balance that the oxygen has to be more oxidized, so closer to -1 than perhaps normal -2 in oxides. So we also conducted an X-ray Raman spectroscopy study to look at the oxygen edge for this compound. Now, this is a very challenging measurement since we cannot access the oxygen edge directly through X-ray absorption. So at 540 EV, the oxygen edge is a soft X-ray measurement and requires vacuum. So we have to do an inelastic measurement and shift both the incident and the scattered X-rays into the hard X-ray regime. And then the difference in the incident and scattered X-ray energy is the oxygen edge. So here, this is the measurement we did on the oxygen K edge for FeO2 at 110 GPa, I think. And the thing to notice here is that you see a significant pi star peak, which would be consistent with increased oxygen-oxygen interactions and the oxygen being more oxidized. Oh, great. Okay, so we can also look at the electronic spin and magnetic behavior of iron-bearing compounds. And so the electronic spin state of iron, the iron 3D electrons, as Renata also showed us earlier today, can be probed by studying the iron K beta fluorescence via X-ray emission spectroscopy. And so what we actually saw is that the intensity of this K beta prime peak, so this little shoulder here, decreases between 45 and 60 GPa, and then it disappears around 60 to 65 GPa. And this indicates the total spin momentum of the iron in this FeO2 phase is approaching 0, and that this phase undergoes a spin pairing transition around 65 GPa from high spin to low spin. And we also heard about synchrotron Mossbauer spectroscopy. And so we collected a series of SMS spectra on the FeO2H compound, and it showed that it's non-magnetic for all the conditions under which it's stable. And you get a single clean single beat spectra, regardless of the content of hydrogen in the lattice. We also analyzed this spectra using the CONUS program to extract the quadrupole splitting and isomer shift of the iron and FeO2. And I guess that would just say the values of the QS and IS of iron in this FeO2H material are, when extrapolated back to ambient conditions, are very close to pyrite. Okay, so could there be any evidence for Fe2H or FeO2 in the Earth's interior? Well, so you've also heard that seismology provides us with our observations of the Earth's deep structure, and that near the core mineral boundary, there are a number of interesting features like ultra low velocity zones and large low shear velocity provinces, which are characterized by increased density and variable depression in shear and compressional wave velocities. And so there have been a number of hypotheses that have been proposed for explaining these features. So why not add another one? So what about FeO2? Well, in order to even see that if it's in the realm of possibility, we need to know the velocity and density of this phase. So Jean also determined the density and the sound velocities for FeO2H and FeO2 using X-ray diffraction coupled with another synchrotron technique, nuclear resonance inelastic X-ray scattering, which Jennifer Jackson discussed in her talk. And what we found was that compared to PREM, we find that the compressional wave velocity is about 20% lower, and the shear wave velocity is about 40% lower, and then the density is about 20 to 30% higher. So so for the ultra low velocity zones, then if we roughly want to match density and velocities, about 50% of this hydrogen bearing iron oxygen rich phase would mix with average mantle, would give you something consistent with ultra low velocity zones. And then maybe 5 to 10% of this material mixed with average mantle would give you something like that's fairly consistent with LLSDPs. Okay, so just to summarize, the main point here is I wanted from this unexpected chemistry in iron and water at deep mantle conditions, we can use multiple synchrotron X-ray probes to study this material. And one of the main findings is that iron and oxygen can potentially have multiple valence states in the lower mantle, as Leonid also had mentioned earlier during this workshop, and that these might be possible candidates for some of the interesting seismic anomalies observed at the base of the mantle. And ultimately, I want to get to answering questions about volatiles in the Earth, like how hydrogen and oxygen, what are the hydrogen and oxygen carriers in the deep mantle, and how are hydrogen and oxygen transported, stored, and cycled through the Earth. Okay, so now I wanted to kind of change gears and show an example of where we use one technique to maybe look at a wide number of deep Earth problems, or the opportunities to use one technique to look at a wide number of problems. So we already heard quite a bit about X-ray imaging. So now I wanted to kind of focus more on the X-ray imaging in a diamond cell. And so for this, we used with a nanoscale transmission X-ray microscope. So it has all the same parts as an X-ray microscope, but I guess one of the key features, especially for diamond animal cell work, is the very, very high spatial resolution. So you can do two-dimensional imaging in both phase and absorption contrast with 30 to 40 nanometer spatial resolution. So this is a figure of a Siemens star calibration pattern. And so these thinnest lines, the width of the thinnest lines here is 30 nanometers. And then here, I just show some work that where we imaged Hadean zircon that we got from Mark Harrison. And so he was interested in looking at these very rare carbonaceous inclusions. And so you actually can see me that it's like a hexagonal shape. So this is actually a graphite inclusion that's within our, within his Hadean zircon. And then with these really nice 2D radiographs, if you can have enough access at different angles, then you can reconstruct the 3D objects, so do 3D tomography. And so this is often really important. And this little movie here kind of shows an extreme case, which demonstrates the importance of having 3D information. So I'll apologize to those who have seen this movie before. I show it very often, but actually really, frankly, I don't think you can watch it too many times. I think it's really brilliant. So it was made by by a beamline scientist at SSRL, Eugene Liu, and it demonstrates that different angles, yes, can look like no. So you really need to do reconstruct the 3D object to really understand, what you're looking at. And another advantage of synchrotron radiation, using synchrotron X-rays as your source, is that you have the possibility of tuning the incident energy, which enables element-specific imaging, so spectroscopic imaging. All right, so we want to be able to conduct 3D imaging at deep Earth conditions. So this picture is here to remind me that this project started pretty serendipitously. I was running an X-ray Raman spectroscopy experiment at SSRL in the second hutch of 6-2. And those experiments take forever. They can take up to days for one pressure measurement. So while I was at the demo, I was getting a little bit bored, and so I started looking around to see what else was going on. And I ran into Piero Pianetta. So this is the picture of him, who was the acting director of SSRL, and he was working in the third hutch and working on this nano TXM instrument. So he very kindly introduced me to the capabilities, and I thought this was very exciting. And so I wrote a beamtime proposal, and we started developing high pressure capabilities. And that was in 2009. So it's kind of scary that it's 2021 now, but that's when we got our first beam time. And so, well, where are we now? We can look at quench samples really well. So these are samples that are synthesized at high pressures and temperatures, and then recovered back to ambient conditions. And we cut out a small portion of our diamond cell sample and image that. We also can couple a diamond enamel cell for in situ high pressure imaging at room temperature. And so here we used a modified diamond cell for that purpose, because for tomography, if we want to do tomography, then we need to have as much side access as possible. So we want 180 degrees would be ideal, because that would give you complete access. But with the pins in our diamond cell, then we're limited to, for this cross cell, limited about 160 to 165 degrees access. So we have about 15, 20 degrees of missing angle. And then we direct our X-ray beam perpendicular to the diamond axis. And so we use an X-ray transparent gasket like beryllium. And then future developments, which it's still on my list of things to do, is to try to get in situ high pressure and high temperature, realizing that this is very important for deep Earth studies, in situ deep Earth studies. Okay, so so briefly I want to show some examples of where we use the nano-TXM to look at some studies. So here's one where we looked at core formation mechanisms. Won't say too much here. So a number of mechanisms have been proposed for how the iron-rich core separated from the silicate mantle, including magma ocean, diapirism, percolation, deformation. And of course, it's not necessarily one mechanism versus another. And you can also have multiple processes operating together at different pressure and temperature conditions during Earth's history. But if we want to get beyond kind of schematic pictures, we need to have more information about what's going on, the behavior of iron-rich melts with silicate phases at high pressures and temperatures. So I'm going to show some imaging on iron-rich melts and silicates that we quenched from a diamond enamel cell. So this is work that was led by a former graduate student, Crystal Shi. The starting material was a mixture of enstatite and an iron-nickel sulfur alloy. And so Crystal compressed the samples in a diamond cell, reached high temperature using laser heating, and I'll show results from 4 samples. And we also collected high pressure temperature diffraction at APS to confirm that the iron alloy was indeed molten and that we were recrystallizing the silicate in the high pressure bridgmanite phase. We then recovered the sample back to ambient conditions and cut out a region of interest using FIB. And then we imaged the section using the nano-TXM. And then as a further benchmark, we also took a portion of the FIB sample, and Faye and his group at Carnegie helped us with serial sectioning via FIB-SEM. Oh, too many. Okay, so here are the results for the 3D melt, the 3D distribution of iron alloy melt in bridgmanite synthesized at 25 GPa, 39 GPa, 52 GPa, and 64 GPa. And so the red portions are iron alloy, and then the gray portions show the silicate, surrounding silicate matrix. And I think the first thing to notice is that there's a dramatic change in the iron distribution from isolated pockets to interconnected networks. And so this demonstrates that iron may be able to form an interconnected network between bridgmanite grain boundaries around 40 to 50 GPa. And then we also see that the molten iron is efficiently wetting the surface of the silicate grains. You can almost see them outlining them. So we see a pretty dramatic change in the potential percolative ability. And then just a summary, which also shows the smaller portion of the FIB SEM. We can compare our TXMs to the serial sectioning approach, and they are consistent, so that's great. So this is where you use an FIB, SEM image, FIB cut off a layer, SEM image, FIB layer, on to reconstruct a 3D image from many 2D images. Sorry, 3D object from many 2D images. And so the resolution for both techniques is pretty similar. SEM has a benefit in the 2 dimensions, but you lose some in the fibbing direction. Also, a benefit of nano-TXM is that you can look at a larger sample faster, and that is a potential for in situ, complex environments and looking at imaging things in situ. All right. Okay. Sorry, very briefly then I'll also show some other examples of actual in situ high pressure studies with the nano-TXM in a diamond cell. So for these, you could look at equation of state of amorphous materials and hopefully melt, so if we can ever get this high temperature stuff working. So we looked at you can just directly measure the volume of a glass as it changes, as you compress it. So Yulin, who is my first graduate student and now staff scientist at SLAC, she looked at Germania glass, which is kind of prototypical network forming oxide glass, also the analog for SiO2. And also the germanium K edge is near 11 keV, so it provides very good absorption contrast if you want to do absorption, use absorption for imaging the object. Okay, so she used FIB to cut 40 by 40 by 40 cube of GO2, and then we did the imaging at different pressures, and then these are some 3D renderings at 0.4 up to almost 40 GPa. So we can use the results to get a pressure volume relationship. And so what we find is that the density data appears to be display a continuous trend to the highest pressure, but there's a change in compressibility around 10 to 13 GPa. And this complements XF data that we also collected we had previously collected on GO2 at high pressure, where found that GO2 undergoes a coordination change from 4-fold to 6-fold around this pressure. Okay, so emboldened by the success, we began looking at more Earth-relevant compositions like SiO2 and silicate glasses. But these are made up of elements that don't have a lot of electrons, so it's more challenging to get good absorption contrast at the energies we're looking at. So in early experiments, we tried coating our SiO2 cubes with a thin layer of platinum. So this cube was initially 15 by 15 by 15 microns, and then we coated it with some platinum. It's hard to get even coating, so that's why you see some of the SiO2 poking out here. And so what Jean found was that difference between 30 GPa and 1.3 GPa, we saw a volume reduction of 2-fold. We became pretty concerned that the platinum layer might be doing something to or might be changing how the volume changes with high pressure, influencing the equation of state. So we also just cut discs of SiO2, where the disc is about 15 microns thick and 40 microns in diameter. And he tried imaging that without a coating. That actually also worked pretty well. So both the uncoated and coated results give pretty consistent results. And there's a change in compressibility at 30 GPa in our SiO2 results, but we're still working on that, and also some other silicate glass work. Okay, and then very quickly, I wanted to say that you can also do spectroscopy plus TXM. So in this case, because with their synchrotron source, you can tune energy, you can get a dramatic increase in absorption and compare the absorption right below and right above an edge to really enhance elements of interest. So if we look at like the iron, like images below and above the iron edge, then you can see for this sample, that's a mixture of silicate in the blue and red iron alloy, that the iron blobs kind of immediately pop out when we look at the difference between below and above iron edge imaging. Okay, so we can use this to look at how the oxidation state might be changing during a pressure-induced charge transfer transition. So this is what we looked at in bismuth nickel oxide. So at low pressure, you have nickel in both 2+ and bismuth. So you have nickel in 2+, bismuth in both 3+ and 5+. So it's mixed valence. Below 4 GPa, and then just below 4 GPa, so just around 4 GPa, you get charge transfer from nickel to bismuth, and then results in just nickel 3+ and bismuth 3+. And so you can follow these changes by looking at the nickel K edge. And so with a 3D spectroscopic imaging, you can see how the sample is transforming in 3D, and then follow this kind of pressure-induced redox reaction in 3 dimensions with pressure. Okay, so briefly, I now wanted to discuss some opportunities for using X-ray free electron lasers for high pressure X-ray studies. Now there are a number of hard X-ray free electron lasers currently operational worldwide. And so we just take a look at, oh, sorry. What was that? Okay.
Continue.
1 minute. Okay. So, sorry. So very briefly, then you just see that the main thing to notice is that they're exceptional peak brightness. So about 9 orders of magnitude brighter than third generation sources. Although now I guess we have to bump up ESRF and we'll have to bump up APS by 2 orders of magnitude, but still, millions or hundreds of million times brighter. Peak brightness, very large number of photons per bunch, short pulse durations of 50 femtoseconds, and tunable energy, highly coherent. So you can use the matter in extreme conditions instrument, MEC, to couple this very fast X-ray bunch with dynamic compression. So you can generate a shock using optical lasers and then follow how property is changing using the X-rays as the shock is propagating. So you can use ultra fast diffraction. And so this is a study led by Ariana Gleason, where she looked at how silica changes as the shock propagates it through it. Okay, so these are just at 0 nanoseconds, no shock. It's a silica glass, so you don't see any diffraction pattern. And then 11.6 nanoseconds later, the shock is in the sample, and you can see that you've crystallized stishovite. And so you have these smooth rings that correspond to octahedrally coordinated SiO2. And then you can integrate many patterns at different laser powers over different time delays to get information on grain growth and phase transitions in silica. You can also do ultra-fast radial X-ray diffraction. So we've heard talks about radial diffraction at a diamond anvil cell. We can also use a similar geometry where we have our pump laser close to 90 degrees to our probe X-rays, and then see how the texture development and lattice strains change with azimuth angle. And so this is a study that was led by Sebastian Merkel. And so I'm not going to have time to talk about it, but I will just say that if you're interested, Sebastian's going to present something at AGU, but it's another capability that you can do using XFEL. So a lot of the measurements we were able to do at Synchrotron can now be done at X-ray free electron laser. Okay, so there's some interesting work here that I unfortunately don't have time to talk about. And then Guillaume already also discussed the capability of doing coupling X-ray emission with X-ray diffraction and an XFEL. And so I'll pass this on to Dan because he's going to write a paper. He's writing a paper that we're on that will hopefully get submitted soon, but he'll also be presenting at fall AGU. But the point here is that in single shot X-ray, we can collect single shot X-ray emission spectra and single shot X-ray diffraction spectra on the same sample. And this enables you to see the spin transition and structural transitions in the same shot. And because we're using laser shock compression and this ultra fast timescales, we've actually been able to look at melt. So here's some X-ray emission spectra from olivine melt that's been shock compressed to 104 GPa and 200 GPa. Okay, so very briefly, I want to talk about touch on future vision. And so this involves both very impressive how rapidly all the sources are being upgraded and changing. And so I won't say anything about the third generation sources. We already heard about ESRF, EBS, and then planned APS-U upgrades. So I think having this much smaller divergence and higher brightness is going to be pretty exciting opportunity. Also LCLS2 has happened. So there's an upgrade to higher frequency, so 1 megahertz, which allows higher brightness, so something that's similar to the European XFEL, and that there's plans to also push it to higher energy, which was very important for our community to actually get to the 10 keV range. So I just wanted to also say that we can actually go to high energy now, but at lower frequency, which is okay for our shock experiments. So I wanted to say a little bit about access, but maybe I don't need to say anything because we've already discussed. This has already been discussed. And I think one of the lessons from COVID is actually that remote capabilities, and as many people have mentioned, do work. like it can work and be very efficient. And of course, this is remote in our sense, but for the beamline scientists, it's not remote. It's much more work for them, but it has demonstrated that actually remote capabilities are pretty exciting. And it's something that we should really think about how we can put in more resources to make them effective and not to burn out all the fantastic beamline staff doing them, because it can broaden accessibility and training. And so I was just thinking, because Anand had mentioned that there's a two-pronged approach for different kinds of what we should be thinking about study-wise, but I think also experiment-wise, it's like two prongs, right? Kind of performance workhorse experiments where we really move towards remote and automation, like protein crystallography model, and then also have that balance with some innovation experiments, which are high risk, high gain, long-term collaborations, development of new techniques. Okay, so sorry I ran over, but I'm done. And acknowledgements to many of the co-workers, and thank you.
Oh, you're perfect, Wendy. We have plenty of time for a question from Guillaume.
Great.
Yeah, just thanks a lot, Wendy, for the presentation. It was very nice to see all this work, really.
Sorry, I shortchanged our collaboration, Gil.
No problem for that. No, I was wondering for the 3D tomography, if you can have access to the chemical information that you will have when you do the FIB. One of the things is you can have all the chemical mapping, and what are the, could you do chemical mapping at the same time as the 3D really detail?
Absolutely. It's just that changing between elemental edges can be a little bit tricky, because at the instrument that we're using is 4 to 14 kV. So sometimes you're looking at some L edges, sometimes you're looking at K edges, but absolutely, you can look at chemical information, oxidation state information, as long as at high pressure, you have reasonable understanding of how the absorption edge changes. You can fit it. As long as it's mostly, I think a lot of it is standard.
But you do that with the absorption edge. I was wondering if there is also, for example, with diffraction, you can have kind of idea of the chemistry, or also using I don't know, or X-ray fluorescence or other type of diagnostic.
I think that would definitely be possible. It's just that at the beamline that we're using, X-ray absorption is a pretty easy one, since you're using energy anyways. You're just looking at how much it absorbs at this energy. But absolutely anything that's diagnostic of an element, and you could think about just having the right detector to look at that, right?
Okay. Thanks.
And a lot of that too is a big limitation is software, because now can you imagine you're collecting all this 3D information, all these different energies. I think one of the really rate limiting thing about pictures and movies is this data problem. It's like total fire hose of data.
Great, thanks. Maybe one quick question from Sean.
Hi, Wendy. Great talk. Just a quick question for you. When you mentioned the X-ray Raman spectroscopy, what would be the smallest sample the beamline can probe?
So the beam isn't so big. I think the problem is the beam size versus also the background, and if anything is in there. So at every sample, as you get to higher pressure, it becomes very thin. And so for some of these a lot of these samples, we're looking perpendicular to the diamond axis. So even if you have a large sample, it's still going to be a thin sample if you go to high pressure. And so that becomes a problem. And so you're going to get absorption from diamond and even background from diamond, depending on what edge you're looking at. So our samples typically like 30 to 50 micron size. The one that Jean looked at was quite a bit smaller because it was 110 GPa, but that kind of noisy spectra took 4 days of beam time to collect that one spectra. So it's a challenge, I would say. And so actually one more thing I wanted to say with the XFEL, with the increased brightness, so even just at the synchrotron, 100 times brighter, absolutely, X-ray Raman will be completely a game changer for X-ray Raman. But the XFEL too, with the high energy upgrade, it'll also be like maybe 1,000,000 times brighter, average brightness. That also would make a huge difference for all of these photon-starved inelastic X-ray scattering measurements.
Okay, thank you.
Thanks.
Thanks again, Wendy.